symmetry, we have x-axis symmetry, y-axis symmetry, and origin symmetry. And so a lot of the functions you've studied already have symmetry. Symmetry just means it's picture in terms of geometric terms, or in real life it's taking one half and folding it over the other and making it match. Then it is symmetric. So lots of things in life are symmetric. Lots of functions are symmetric. And here's the definition of x-axis symmetry. If xy is on the graph, then x negative y is 2. I can show you what I mean by that. Let's write it down first. So if xy is on the graph, then x negative y is 2. So let's just pull up a graphing grid. I'll show you what I mean. Oops, is that gonna work? I'm going to do a separate one here. All right, so an example would be, let's pick a point x comma y, say 3 comma 2. Okay? So if 3 comma 2 is on the graph, so go over 3 and up 2, to be x-axis symmetric, then, so this is 3 comma 2. What the definition said is that, that's positive 2. It's 3 comma 2. The definition said that if 3 comma 2 is on the graph, then also 3 comma negative 2 is on the graph. So 3 comma negative 2 is on the graph, right? And if, say 1 comma negative 1 was on the graph, what's the opposite of negative 1? Positive 1. So 1 comma 1 would be on the graph. And if, say, 0, 0 were on the graph, then also 0, 0 would be on the graph. Yeah, the opposite of 0 is still 0. So does this look kind of familiar? Here's your example of x-axis symmetry, right? So side is parabola as well. Okay. So that's what that definition is saying. It's saying it in more general terms, point by point. Because you don't have to have a continuous function to have, that symmetry. You could have, same points above and points below that are symmetric to each other. You could fold one half over the other, and the points would match up, as opposed to the whole curve. Okay. So let's go back over to here. Y-axis symmetry, we call this an even function. So x-axis symmetry, probably the best example is a sideways parabola. Y-axis symmetry, this one is even more familiar. If xy is on the graph, then negative x comma y is too. So let's write that down. If xy is on the graph, then negative x comma y is. All right. Origin symmetry. If xy is on the graph, then negative x, negative y is 2. So if xy is on the graph, negative x, negative y is 2. Origin symmetric would be like a double flip, like flipping over the x and the y. A little harder to picture. But I'm going to show you how to not just tell if things are x-axis symmetric, or we're going to actually call these even and odd, but it's equivalent to y-axis symmetric and origin symmetric algebraically. There's a way to do that algebraically. And then also you can do it visually if you graph it. Like if you graph it on your graphing calculator, it's pretty easy to tell if it's x-axis symmetric or y-axis symmetric. Origin symmetric may not be quite as easy. It involves the double flip, double reflection. So to determine the symmetry algebraically, here's what we do, and you may have done this last year. You look at the equation here, the function. Here's number 1. And if you're going to test for each, we really don't want to test for each one. It's kind of nice if you have an idea of which one it might be. For example, to be even, what this is saying is that you get the same y output regardless of whether you put x or negative x in. So if that's true, what types of things would you be looking at in the function to think that, hey, this might actually be even? What kinds of features of the function would make roots? Roots, okay, you're on the right track. It's actually the inverse of roots. Yeah. Exponents, what kinds of exponents will take a negative x, and when you, even, when you square it or take it to the fourth, it's going to give the same thing as an output, right? So we could go through a process in which we test every one of them. There's basically 3 of them in your book. Your textbook, it lists them as well. But here they are. You can replace x with negative x. Maybe write these down here. These are the 3 tests. So for y-axis symmetry, you replace x with negative x, and if you get the same equation, then it's even or y-axis symmetric. For odd, when it comes for odd or for origin symmetry, you replace both. So you replace x with negative x, and you replace y with negative y, and then you see if you get the same equation that you started with. Okay. And then for x-axis symmetry, what do you think you have to do on that one? Replace y with negative y and see if you get the same equation. Did you do this at all last year? Test for even or oddness? Yeah. Okay. So these are the 3 tests. Now, you can, if you're looking at this function, you're not sure even which of these categories it falls into, then you just have to try out 3. Okay. But I'm looking at this thinking, hey, I see a couple of x squareds in here. I'll bet it's even, right? I'll bet that's the one. So this is one where I would replace x with negative x and just demonstrate that, yes, it is in fact even. I can tell it's even by looking at it. Because when I plug in negative x for x here, I'm just going to get a positive x squared. So just write on there, replace x with negative x, and we have y equals negative x squared minus 4. So really what I'm doing is a proof. I'm looking at this saying it looks like it's even, okay, or y-axis symmetric, and I'm plugging in. So negative x squared plus 1, and that gives me x squared minus 4 over x squared plus 1. This one right here we would say is even. And it's even because when I replaced x with negative x, I got the same equation back. Okay. All right, let's test this next one here. What's your hunch on this next one? So we don't have to test all of them. What do you think it'll be? Think it's x-axis symmetric, y-axis symmetric, or origin symmetric? It might be x-axis symmetric. And what makes you think that? Because the y is squared. So plugging in a negative y for y is probably not going to change the equation yet. So, and you're right. So replace, on this one we're going to replace y with negative y and see what happens. So it's negative y squared equals x plus 3. So I have y squared equals x plus 3. And so since this is exactly the same as this, after replacing y with negative y, and we have x-axis symmetry. So we had one that had y-axis symmetry, or was called even. Actually, as we move into calculus, we use the terms even and odd more often because that tells us about, it gives us information about the domain and range of the function, tells us about the function. But the even is same as y-axis symmetry, so those are interchangeable. And then x-axis symmetry, it doesn't fit into the even or the odd category. It's just x-axis symmetric. We would call that a neither. If you were asked, is the function even or odd, you would say neither. It's neither even nor odd. And then, what about this one for number 3? It's a cubic. You have a guess as to which type of symmetry it might have? Yeah, this is going to be the origin example, yeah. Because if I can't just replace negative y and keep the equation the same. I can't just replace x with negative x and keep it the same. But if I replace both, the negatives will cancel and keep it the same. So, like I said, if you're not sure, you just have to try each of these. Okay, so it's helpful to just look at it first. Say, okay, I'm going to try replacing x with negative x and y with negative y. And then see what happens. So negative y equals cubed root of negative x. Every time I plug in a negative y or a negative x for an x or a y, I put it in parentheses. And that'll help you with your order of operations. If you leave the parentheses out, you might mess up your sign. And so negative y just stays negative y. Cubed root of negative x is actually negative cubed root of x. You could pull the negative 1 out. And so y equals cubed root of x. That negative sign is for the whole cubed root, and those cancel out. So this one is an example of odd or origin symmetric. Alright, this one, number 4, may take some thought. Take a little bit of thought. Had one of each. Anybody, as you're looking at it, anybody have an idea of what it might be? You have a reason? You have a guess. You're thinking. What are you thinking?
I'm thinking since I guess.
Sure. This one's not obvious. We might just have to go through all 3. Yeah, Jess?
Would it be even because the odd x with the power would cancel if the y was switched and then we just have the positive?
Yeah, that's kind of in line with what we just did. As you're thinking that odd x would cancel with maybe the odd y, is that okay? That is kind of like what we did on the origin one, though, in terms of that canceling. Yeah, that's the type of thinking that it takes. And then the x to the 4th is going to stay the same. Well, anybody else have any other ideas? So we might just have to go through and try each one. So if we replace this one, it's the same as the one before it here. This one, if we replace y with negative y and x with negative x, we do get the same equation back. So it is odd or origin symmetric. Any questions on that so far? All right, it says complete the graph so the equation has the indicated symmetry. If this is going to be even, we would just draw in that second half there. Odd, here's what I mean by the double reflection. This is actually the sine curve. It looks like the sine curve. It says that, well, if we go down, it's going to come up again here. And then back down. So it's like taking this and flipping it over the y-axis and then again over the x-axis. So it's like a double flip to get that odd one there. And then x-axis symmetry is just folding it over the x-axis. That's pretty easy to see. So there's a visual on those. Yeah, y equals x squared, y equals x cubed, y equals 1 over x. We just graphed all of those. When I put these on here just to remind you. You don't need to do these right now. You could draw a quick sketch if you want. But I said check for symmetry, make a t-chart. When in doubt, you can make a t-chart. You know what I mean by a t-chart? If you're not sure what it looks like, say you forgot. I think those three you're probably good on. We just did them. Say you forgot what x equals y squared looks like. Well, we would just draw a t-chart and try some x and y values. Just plug them in and start seeing what it looks like. So we might try, values for y, maybe 0, 1, and 2. So if I plug in 0 for y, I get 0 for x. If I plug in 1 for y, I get 1 for x. If I plug in 2 for y, I get 4 for x. So what I'm seeing here is half of my sideways parabola. 0, 0, 1, 1, 4, 2. I'm going, hey, wait a minute. I remember what this is. Because if I were to plug in, say, a negative 2 for y, I'm still going to get a positive 4 for x. And then I go, okay, I know what that looks like. So don't be afraid to use a t-chart. It's okay. You know, it seems kind of like you're going back to algebra. Remember algebra 1, every time you're introduced to a new function, it was a t-chart. But it's okay to use a t-chart to get an idea of what it looks like. Plug in some points, and I think that will help you. Any questions on that?